Hello! So I've been wanting to make a modular origami dodecahedron. This video will show how I went about designing, folding, and assembling this stellated dodecahedron from 30 individual square sheets of origami paper. In origami, other polyhedra can be easily constructed with a module known as the Sonobe unit. This module consists of a strip of 4 right isosceles triangles that can interlock, where the distal triangles fit into the middle triangle's pockets. You can make trimers from these. These trimers are super versatile. The smallest solid you can make from these is a 6-faced object with one Sonobe trimer, which I like to think of as being a 3D projection of a 4 simplex. The interlocking modules all stay together without glue or any fasteners. With 2 trimers, or 6 units, you can make a cube. After all, a square is simply just 2 right isosceles triangles joined together at the hypotenuse. With 12 units, you can make a stellated octahedron. And with 30, you can make a stellated icosahedron, one of my favorites. So naturally, the next interesting polyhedron to make is a stellated dodecahedron, a solid with 12 pentagonal faces, each composed of 5 triangular facets. Notably, the dodecahedron is the dual of the icosahedron, whereby faces and vertices are duals of each other. That is, a face's center point in one corresponds to the vertex in the other. So this feels like it should be doable with Sonobe units, right? Well, you'll notice that this one here isn't actually built from Sonobe units. It looks different. Now this is where things get interesting, because we want to make pentamers from our Sonobe units. But remember that they are right isosceles triangles. But 5 times the 90-degree angle we'd have for each face's apex is greater than 360 degrees. The math's not mathing. The solution, naturally, is to reduce our apex angle. Why not 60 degrees? In other words, we need equilateral triangles. In this initial attempt, I have something analogous to the Sonobe module, but with these ugly flaps, and crucially, only 1/4 of each face is a pocket, as opposed to half of each face on the Sonobe module. This makes it feel pretty flimsy. So, since I was taking the opportunity to design a new module, I wanted something a bit more durable and elegant. This is what I came up with. I'm sure similar units have been developed before, but this is a design that I came up with while playing around with paper late at night. So, instead of a 4-face unit, I wanted to try 6, so that you could fit these in a way where 2 modules would interlock on 2 separate faces. It would be nice and strong. So how does one go about folding this? Before getting into the weeds, to summarize, first, we start by taking a sheet of paper. Thin paper is your friend, since there will be a lot of internal layering which adds thickness, and a lot of overlapping during assembly. We'll then crease the paper into an iso grid. I'll show some nice tricks for this. We'll be thinking about these 6 triangles as our resulting faces as we go through assembly. We then keep folding to get our final units. These units have chirality, so if you want to be interesting, you can create the stereoisomer to this module, but of course, all 30 modules have to be of the same chirality. The units then get assembled into the stellated dodecahedron. It is easy to think of these as being constructed from pentamers. Now let's actually do this. Start by creasing the sheet in half lengthwise, and then crease each of these resulting halves yet again. Now we need to start creasing off-axis to start constructing the iso grid. Take one corner and bring it up to the center crease, where the bottom left corner will be one end of the fold. Make sure your folds are crisp and precise. We will now mirror what we just did. Note how different parts of the existing creases are already aligning with each other. And with that, we have our first equilateral triangles. Now bring the corner up to where these creases intersect and fold. Again, we will mirror this on the other side. Now comes a more technical fold. Partially lift up one of the flaps and bring the edge of the paper into the crease to create yet another off-axis fold. Make sure everything intersects neatly. You'll get sick of hearing this, but now we will mirror this fold on the other side. Our iso grid is nicely coming together. The next two folds will complete it. Bring the bottom end of this off-axis crease to this intersection, mirroring this for the last crease. Like I mentioned earlier, these 6 triangles will be our resulting unit's faces. Now let's fold the square sheet down. Fully fold the short top left crease and fold in half again. Fold once more along the existing crease. Now fold along the opposite side's crease and fold this little flappy thing back. Like on the other side, we will fold this in half again and fold again along the next crease. Things are starting to take shape. Now we need to just manage the ends. Unfold the top side to reveal this crease. Fold it, and then refold the top side. Now we need to do something similar on the other side. But we're asymmetric since we started from a square sheet and we're somehow turning it into equilateral triangles, so the crease that we need to fold is a bit different. Once we're done, we have our strip of 6 equilateral triangles. Now time for the final creases that will complete our module. Make a valley fold along the middle and mountain folds for the other triangles. And there we have it, a module that's ready for assembly into the larger piece. For assembly, each unit will contribute to 1/5 of each of 2 pentamers, 3 triangles in one and 3 in the other. This is how 2 units interlock. Remember, each end shares 2 faces with another module. When everything comes together, this ends up being a pretty strong connection, but can be a little bit tricky to deal with while it's all coming together. You can keep adding units to a starting pentamer, iteratively building up the stellated dodecahedron. You'll find that some module placements are easier than others. Ultimately, 30 modules later, you will get the finished product. Inserting the last few modules can be a bit tricky, but I found that using a pair of hemostats helped pull things in the right direction. As a freebie, if you have some extra paper on hand, you can make a tetrachus hexahedron in a similar fashion by using tetramers instead of pentamers. Look, it's so teensy and cute. So that's how you can create a stellated dodecahedron from 30 sheets of paper folded into identical modules. Now you can get the ball rolling on your own. Thanks for watching.